Hi, my name is Oliver, and today I'll be showcasing our CS152 project. The group members are me, Max Rose, and Antonio Revilla. So today we want to show how we can train a neural network to solve a maze. So here in the top right hand corner we see our Unreal Engine maze. And what we want to do is we want to pass in images to our neural network such that it can recognize these signals. The signals are going to be depicted as arrows indicating to move left or right. This one is a right arrow, this one is a left arrow. So what we care a lot in this project is image recognition as opposed to maze navigation. And we want to train a neural network such that it can reach the end goal, which is the blue box here. Now, this is just example of one maze. We made a algorithm, not an algorithm, we used a file that uses an algorithm to generate the mazes. And we generated 20 mazes, 20 training mazes, 20 validation mazes, and they're all the same dimensions. They're all square mazes, but they don't need to be square. They can be m by n, but we chose square mazes for simplicity. So one question to ask is, how did we collect images for this model? And the way we collected images was by creating a bot, an automator, to traverse through the mazes automatically. Now, at first, this project is also done in relation to the ARCS lab summer's research in the summer. And what they found is that straight, perfect mazes, perfect 90-degree angles, perfect straight lines, that sort of training data produced poor neural networks because the neural networks couldn't recognize how to move in a new maze. So thanks to Jared Mejia, he wrote some automator code which induced random noise into the turn angles. That way, we solve the maze imperfectly, but we still solve it. We just add some noise so the neural network can recognize where to move in a new environment. So the code Jared wrote was for the raycasting simulation. However, since we're working in the Unreal simulation, we needed to adapt this code. And the way we adapted it, the biggest difference was by changing the simulation environments. So in this line here specifically, instead of calling a raycasting environment, what we're going to do is we're going to instantiate an Unreal environment. And the way we do that is by calling a wrapper class that we wrote. And this wrapper class is going to establish a connection from the Jupyter Notebook to the Unreal Engine game. And once we establish that connection, once we instantiate the Unreal Engine object, then we can change out the code such that we call Unreal Engine methods on that object. So we'll demonstrate that a little bit. So here's our Unreal Engine utils class. This class is basically defining the object and methods for the Unreal Engine wrapper. And I want to highlight some differences here. The first of which being is that in the Unreal Engine maze, the start coordinates are 700 and negative 700, whereas in raycasting, they're 1.5 and 1.5. Turn speeds are a little different. And so the basic goal between the wrapper class is to adapt raycasting coordinates to Unreal coordinates. And what we also found was that the Unreal coordinates have a flipped north, south, east, west pole coordinate system. So that threw a wrench in the system. That was challenging. And the way we addressed that was basically doing some geometry. Yeah, we basically did geometry to address the differences in the coordinate systems. But once we got that out of the way, we were able to run the automator, and we collected 10,000 images. And these images, while they're not perfect, they get the job done. They definitely induce noise well enough. We'll show that more on that later. So once we've collected the images, we can now train neural networks in them. So this is what our notebook right here is doing, and we opted to use the FastAI library. FastAI is a machine learning library, and it's basically a wrapper library for the PyTorch library. The reason why we're using FastAI is just because it's simple, robust, and convenient. So now here are the 5 models we want to look at. The 5 models being XResNext18, XResNext50, AlexNet, DensNet121, and ResNet34. We chose these models because these were the best architectures in the raycasting simulation. Over the summer, we ran these models in raycasting, and these are the best raycasting models. So that's why we're going to focus on these 5. And one nice thing about this selection is that they're not necessarily similar. What I mean by that is that DensNet121 is considered a heavyweight network, whereas ResNet34 or even AlexNet is lighter, in that they don't the architectural properties are different in terms of layers. So what I'm going to show here is our training method. We call a CNN learner and specify the architecture type. And then we train for 8 epochs. Now, here we demonstrate the training loss and valid loss. And the nice thing is, for all of these models, there was never an instance where we saw overfitting. Both training loss and valid loss seem to be decreasing at reasonable rates together. And so once we trained, we show a confusion matrix just for give us an idea of how the models might perform. XResNext18 missed quite a few, mistaking a bunch of left turns instead of forwards. And after we train the models, we export them into the same folder as pickle files for us to use later. XResNext50. So in this one, we saw a little bit better results. Instead of mistaking left image 100 left and it only made 80 mistakes, 54 for right. AlexNet did better, actually. Here we see only made 59 mistakes. DensNet probably did the best, capping out at 52 mistakes for left turns and 41 mistakes for right turns. As with ResNet34 actually did better in the confusion matrix. ResNet34 did better, but not performance-wise. We'll demonstrate that a little bit later. So now, once we've trained the models and exported them, we could imitate them. What we mean by imitate is that we're going to pass in images into these models and and predict where to move. So for this notebook, this notebook is doing the imitation, and we need to just focus on these 2 for loops. This is basically doing the work for us. And what we're saying here is that we want to, for each model inside our folder of models, and for each maze inside our validation mazes, the 20 validation mazes, we're going to instantiate a new Unreal world, and we're going to imitate. So we call this function imitating, and imitating does the heavy work. This is the function right here. And I'll just briefly explain this while loop. And what it's basically saying here is that while we're not at the goal and while we're on the correct path, we're gonna predict a move. So we're gonna pass in our current point of view, we call it the observation. We're gonna pass the observation into our model and get the next move outputted here. So now once we have that, we can tell the world to move forward, left, or right. So I'll demonstrate this actually. So right here, I'm telling AlexNet to imitate on maze 1. And what we're doing, the top right hand corner is showing this in action. Maze 1 is, well, yeah, this is maze 1, but we're passing in the images. So basically, as we're traversing through the maze, we're getting new images from the point of view, and we're passing in those new images into AlexNet. Now, we'll let this run for a while, and we're about to see some pitfalls in the way we've trained these models. We'll see that very quickly. In the meantime, we can talk about what happens once we're done. So this will run until it either gets off the path or we make it to the right goal, or it could also exit if it stays in the same place for too long. And once we get out of this while loop, we then calculate how far it went through the maze. And this code is, we'd like to thank Professor Clark for this code. He used breadth for search to basically help calculate how far our model made it through the maze. And we're going to return that value. Once we return that value, It's actually we're returning a tuple of values and we're appending them to some list. And once we append it to a list, we can write it as a CSV file for us to interpret. So once we've written those CSV files, we're about to make a mistake right about here. Yeah. So in the right here, we saw that the model ran through the wall, and we suspect this happens we suspect the reason why this happens is because in the automation phase, in the data collection phase, since in the Unreal Engine there isn't wall collision, we suspect that some of the automator images also wall clipped. It went through the walls, and as a result, the model learned that it might be okay to also go through walls. So in future iterations of this project, we'd want to make sure we find a way to make model collision work inside the Unreal Engine. And we'd want to make sure the automator is more accurate in that it doesn't run into the wall either. But nonetheless, once this finished running, we append that data to a CSV file, basically. And our CSV file is a list of maze names, and maze completions. So here's some example data. I think the most noteworthy, the best model was definitely our DenseNet 121 networks, capping out at 100% completion a few times. And once we got the CSV file, we were able to do some data analysis. We made plots of the file. And yeah, I think that is all. But yeah, this is our 152 project, and in the future we hope that we can train a model that's good enough to go through the Unreal maze and the raycasting mazes. Oh yeah, that that reminded me, yeah. So we did one more part of the project. We also exported the models, the Unreal Engine models, and we applied them in the raycasting simulation. And long story short, the models do not perform that well. Raycasting looks very different from the Unreal Engine. So in future iterations, we would like to work with generative adversarial networks so that we can sort of merge Unreal and simulation images to look similar enough. And the idea is that we'll train a model that can navigate through both, and with the ultimate goal of creating a model to traverse a maze in real life. But yeah, thank you.